Good.
Okay. All right, so last time what we did was we talked about time-varying vector fields, and because it's quite similar in spirit to what we did, I'll start the lecture today by briefly talking about control systems, and the topic here. Oh, good morning, Summer. Nice of you to join us.
Okay, sorry, thanks.
So we'll talk about control systems, and these are, the topic of these lectures is in principle supposed to be control systems, and we're on lecture 7, and for the first time I'm talking about control theory, and I'm only going to do so for 15 minutes. And really, the reason I'm interjecting this now is just because it is kind of natural to talk about it now because it fits in with the things that we were talking about last time. What we'll do is we'll define the class of control systems, and these are kind of what you would call normal control systems, the kind you're sort of familiar with, but it gives us kind of the target that we're going to use to kind of compare our new flavor of control theory with. Okay? So the idea here is very simple. So we're talking about basically control systems of this form. So let me be slightly better here about this. Okay, and I think actually I typically have been using capital F. All right, so of course C is going to take time and give you a curve in a manifold. Mu is a control. This is going to be in some control space C. So C is going to be a topological space for us here. And F is a map then from M cross C into Tm with the property that f of x and u is in the tangent space at x. Okay? All right, so what we're interested in here is what are the properties of this map? Okay? This can't just be some arbitrary map. There has to be some joint continuity properties of f as a function of x and of u, which ensure, for example, that a differential equation like this should have solutions. Okay, and so we're going to. There's two ways to go about doing this. You can prescribe conditions on f as a function of x and u. Okay. Or you can do what we're actually going to do, which is prescribe. So we have then you have the map, let's call it f hat, from C into gamma nu Tm. Okay, so nu here is what nu always is. Okay, so nu is m plus lib infinity omega. I guess you could talk about holomorphic control systems as well. Okay, and so given a map like this, you're going to get a map like so, and so f hat of u. So I'm telling you that that's going to be a vector field, and so it's going to be of class C nu. Okay, so what that means is that for fixed u, as a function of x, it should be class C nu, but we're going to have more properties than just that, but you need at least that. Okay, and this map is going to be then evaluated at a point x. This is, of course, f of x u. Okay, so for a given f, you have a map from the space of controls into the set of vector fields. Okay? And so what we do is we prescribe the properties of this map. Okay, so it's a triple, M, F, and C, where there are all these things that I talked about. So okay, and F. Okay, so the third property here is really the interesting thing, and that's really what tells us what are the properties of this map. Okay, so what I require is I require the map f hat, okay, from controls the space, the control set into the space of vector fields. I require that map to be continuous. Okay, so there is a way of describing pointwise conditions on X and U, that are equivalent to the continuity of that map, and those conditions involve the semi-norms for the topology here. Okay, but I won't write them down there. Let me tell you, just as sort of a point of reference, what those are in the smooth case. Okay, so in the smooth case, condition 3 is equivalent to the following thing. It's equivalent to the condition that, so remember that for fixed u, okay, as a function of x, for nu equals infinity, it's smooth. Okay, so we always have that condition. That just makes it so that this map f hat is well defined. Okay, the requirement that f hat be continuous is exactly the condition that all derivatives depend continuously on x and u. That's the condition for a smooth control system. Okay, and of course, you know, for finitely differentiable, continuity of the however many derivatives you have, and the Lipschitz thing requires you to fiddle with dilatation, and the analytic case is the pointwise characterization is a little bit complicated. Okay, but it amounts to just continuity of that map. So that's kind of the slickest way to say that. Okay, so you know, when Rob is describing his conditions on the little f that he has in his lectures, it's really some kind of C nu condition on the control system. Okay. All right. Now, okay, why is this a good definition? This is a good definition for the following reason. Okay, so first of all, we should, what do we want really to have be true here? As a minimum, what we need is that if you prescribe a reasonable class of controls, right, then you should have existence and uniqueness of solutions of this differential equation. Okay, so what's a good class of controls here? Well, we have a topological space, so integrable does not a priori make sense. Okay, but bounded does. Okay. So we consider locally, essentially, bounded controls, mu. Okay, so these will go from some. So remember, I introduced this idea last time that this t will be an interval, okay, into C. All right. So what this means is for every compact subinterval t prime in T, okay, there exists a compact set K in the control set C such that, okay, such that the Lebesgue measure of the set of times, okay, for which mu, okay, so these are the times in this compact subinterval T prime, so that mu is outside K. Is 0. Okay, so for almost every t, the controls take values in this compact set K. That's what I mean by locally essentially bounded. Okay, so that's the, of course, so that's the essentially bounded part, but you also need for these things to be measurable. Okay, so mu is measurable. Okay, so this means the preimages of Borel sets are Lebesgue measurable. Okay, so that's the class of controls that we're going to consider. And then you have, for this class of controls, that if you plug in a control like this into F, okay, then what you get is a time-varying vector field. That time-varying vector field is of the kind that we introduced last time. Okay. So if sigma equals mfc is a C new control system, so the way you would say this is that, so when I say bounded here, I mean bounded in the compact Bornology, right? So that's what it means to be bounded in the compact Bornology. Okay. And if mu is locally essentially bounded, okay, then the mapping. Okay, so what I'm going to get is I'm going to get a mapping which takes a time and a point x. Okay, so this will be in my time domain t across m. Okay, and what it's going to give me is it's going to send me to f of x u of t. Okay, so this will be an element of that tangent space. Okay, all right, so I have this mapping. This is then some sort of a time-varying vector field, right? And so the fact is that this vector field is of the class that we defined last time. It's locally, essentially, C nu bounded. Okay, the notation we used was like this. Okay. All right, so this meant that as a mapping from T into the space of vector fields of class C nu, this map is measurable. Okay, and bounded in the von Neumann Bornology. Okay. All right. So therefore, okay, because locally essentially bounded things are locally integrally bounded. Okay. That's just by definitions of those two objects. Okay. This means that this time-varying vector field that I defined here, because of what I said last time, integral curves exist, are unique, locally exist, are unique, and depend in a C nu manner on initial condition. Okay. All right, so that's the nice, and this theorem is relatively easy to prove. The thing that makes it important is exactly that for every nu, this gives you a natural way of defining what you mean by a C nu control system. Okay, and in the analytic case, this definition gives you a class of control systems that I believe is the correct class of control systems. All right, so if you're going to talk about a C omega control system, this is what you should mean. Okay, and it has these nice properties again about what the flows of the open loop systems look like. Okay, the solutions exist, unique, and depend on initial condition in a C nu manner. Right? Now, in the smooth case, this is something that this definition isn't new. Okay, And if you look at a lot of sort of basic fundamental treatments of nonlinear control theory, what you'll see is that the class of systems that people are talking about are something like C1 or C-lip, okay, or C1 plus lip, things like that. So for example, if you look at Pontryagin's book on optimal control theory, he's talking about C1 control systems. Okay, so this definition sort of includes all the places where people actually have talked carefully about what they mean by regularity of a control system, and extends those definitions to the analytic case. All right, so about the analytic case, let me say something that very much relates to something that we had last time. So in the analytic case, to check sort of continuity of this map f hat, okay, so we have this map f hat from the space of controls into, let's just think of the analytic case, into the space of analytic vector fields. Okay, so to check continuity of this thing is a priori unpleasant because you have to check continuity for a large number of semi-norms, right? Because in the analytic case, you have these semi-norms that are indexed by compact set and by sequence of positive real numbers converging to zero. So it's, in principle, not an easy thing to check. However, if you want to check this in practice, what would you like to do? What you would like to do is you would like to just replace x with z. Okay, so complexify, and then check that the complexification is a holomorphic control system. Right, that's what you'd like to be able to do. And the question is, does that actually capture the actual properties of what I would call an analytic control system? And the answer is it does. In the following sense. Okay. All right, so there's two parts of the result. One part is, if you take a holomorphic control system which restricts to an analytic control system, you can ask, that restricts to some real control system, you can ask, is that real control system a C omega control system? Okay, then you can kind of go the other way. If you're given a C omega control system, can you complexify it to a holomorphic control system? Okay, so there's two parts of the result. Okay, and so if you have a holomorphic control system, and you restrict it to when you restrict it to the real manifold is a real control system, it will be C omega. Okay, so let me see if I can find a way to say that. All right, so I'm assuming that I have a complexification M bar, okay, and okay, I'm assuming that I have an F bar, okay, which goes from M bar cross C into T M bar, okay? And F bar has the property that when I restrict to M, okay, I get real vector fields, so they take values in Tm, all right? So that's what I'm going to start with. Okay, so if we have a holomorphic let me call it sigma bar equals M bar F bar C, okay, that restricts to to a real control system. Okay, just in exactly the sense that I said, that if you put real x's in here, you get real tangent vectors. Okay, then, okay, sigma bar being a C-Hall control system implies that sigma is a C omega control system. That shouldn't be too awfully surprising. But that's the easy part. All right. Now, so the other part is if you're given a real analytic control system, does it extend to a holomorphic control system? Okay, so let me see if I can say this right. All right, so if the first thing is you need local compactness of the control topological space C. Okay, locally compact. Okay. If right, so I've already said that sigma is a C omega control system. All right, so, okay. All right, so what do I need here? Okay. So, sorry, I think what I want to do here is I want to remove that condition, okay? Because that's actually going to be part of the assumptions or part of the conclusions. So when I say it's a control system, I'm just meaning that F maps M cross C into T into the tangent bundle, and as a function of X, it's analytic. Okay, it doesn't have necessarily the joint continuity properties. Is that clear? Okay. So now I'm going to assume that it's a C omega control system. Okay. Then, for each x u in M cross C, there exists K and so actually let me say it this way. There exists a neighborhood U, okay, and a neighborhood O. Okay, so these are so this is a neighborhood of X. This is a neighborhood of U. Okay, and that's a C like this. Okay, and an F bar, which is a holomorphic extension of this thing. Okay, so you complexify the neighborhood U to a neighborhood U bar in M bar cross O into U bar. Okay, such that okay, U bar F bar O is a holomorphic control system. Okay, and when you restrict it to U, it's C omega. Well, no, it agrees with sigma. Okay, so you can locally extend, is the point. Okay, and that's the best you can do. And so you can come up with counterexamples that show that this is false when the control set is not locally compact. Okay, so local compactness is required here to have this holomorphic extension. And this, so let me just say, so this is very, like I said, this is very much like the holomorphic extension result I gave last time for time-varying vector fields. Okay, and both of these results are derived from properties of tensor products, because I'll just write some stuff on the board just to give you some hint about where you might start with this stuff. Okay. Okay. So let's think about a time-varying vector field like this. So this, it turns out, is relatively easy to show that this thing is isomorphic to some tensor product. Okay, so it's a tensor product of this guy, so the locally integrable time-varying function. So these are just now, to make this clear, these are just now real value functions. Okay, tensored with space of sections. Okay, and now we have to take the correct tensor product. Okay, because remember that this tensor product is going to essentially be formed of finite sums of formal products of things from here with vector fields. So, it's going to be vector fields, finite sums of vector fields, fixed vector fields with fixed locally integrable coefficients. Okay, that's just what the tensor product is. So you have to extend that to allow for sort of infinite sums. Okay, so there's some completion process that you undergo. Okay, and so the completion process depends on a topology. Okay, and the topology is derived from what's called the projective tensor product, and that's what the pi is here, and the hat means completion. Okay, so there's some complicated business about tensor products that goes into the result that I had last time, and then this result. Because basically what you do is you look at, okay, because remember that in the nu equals omega case, this space was obtained more or less as a direct limit of sort of holomorphic things. Okay, and so then you need to invoke some theorems about the way that tensor products interact with direct limits.
Sorry, I think that if we use the other tensor product, injective tensor product, we will get the same result because...
In this case, because nuclearity of that guy, yeah, that's right. But this statement will be true for any locally convex space, in fact. Yeah. Okay. All right, so this is a non-trivial result, okay? And again, the main issue is, you know for sure, okay, that if you take a fixed u, all right, that you can complexify the resulting vector field in x, replace x with z, for a fixed u. The thing that's difficult here is that you have to show that you can do that locally, okay? That for every u in a neighborhood, that extension, u bar, can be chosen uniformly. That's the hard part. Okay. All right, so that's all I wanted to say about control systems. And really, again, the point here is that this gives us a class of control systems. And so when I subsequently say control system, this is the kind of control system that I'm going to be referring to. Okay, so we'll think of control systems defined by a triple like this, and the main point is that this F is defined using our locally convex topologies. Okay. All right, so now we're going to go do something completely different. Okay, so what I'm going to talk about is okay, now there's two reasons that I want to do this. One reason is that the presheaves and sheaves are going to form an essential part of the definition of a tautological control system. However, for the purposes of the immediate discussion, what I'm going to do is I'm going to talk about just time-varying vector fields and properties of time-varying vector fields and their flows, and I'm going to frame that in terms of sheaf theoretic descriptions of vector fields and groupoid descriptions of flows. Okay, and so what we'll see is what I hope to convince you, actually, is that that's the correct way to think about a flow. Okay, it's not, and the reason it's the correct way to think about a flow is that it allows you to get over all of the problems that normally arise due to lack of completeness of flows, right? So if you have a vector field, time varying or not, its flow will generally not be definable for all times. Okay, and so then you have to fuss and, for a fixed initial time and a fixed final time, what's the set of, the subset of the manifold for which the flow can be defined, and so you end up talking about, not one parameter subgroups, but, one parameter pseudo groups, okay? And so groupoids and sheaves give you a very nice way of organizing all of that business, okay? So that's going to be our objective here. And as I said, this will also come up as an integral part of our definition of what we will call a tautological control system. Okay? So this will be a very uncomprehensive treatment of sheaf theory. Okay? Sort of just lasering in on the few little things that we need. And then trying to give enough context that it makes a bit of sense. Okay, so...
I'm sorry, maybe this part 2 also a good justification for...
Localness?
Why we need the
localness, yeah. So, yeah, possibly so, yeah. Okay. All right, but the fact is that this is a completely real analytic thing, and we're making the case that this is the right point of view for all regularity categories, right? Yeah. All right.
So
Yeah.
So for the second part,
Yeah.
can basically the type of generality assume O is relatively compact?
C.
Basically C is.
Oh yeah. So in the proof of this, yeah. Oh, it will be relatively compact. Yes, that's right.
And so the idea is that then you cover it with finite open sets on which such an extension can be done.
Part of the proof looks like that, but really, what you do, there's an analog of this kind of a construction. Where you're talking now about continuous maps, okay? I may struggle with this for just a second, so give me a moment, okay? From a compact set, K, okay, into a, let me make it general to sort of illustrate really where this is coming from. So into a locally convex space V, okay. This is isomorphic to continuous functions on K, taking real values, okay, tensored, but now it's actually a different tensor product. And what do they use here? E? I forget, yeah, E for the injective tensor product. Okay, and again, as Sauer said, in our case, the two tensor products agree. Okay, and that has to do with some specific properties of our locally convex spaces of vector fields with V. So again, so for part of this, you need this, and again, you use, and that's where local compactness comes in, because you choose K to be the closure of a locally compact neighborhood, right? So that gets you your local. So part of it, you do a covering argument, but for the other part, you don't. Yeah. Okay. But again, the hard thing, even in the little neighborhood and cover definition, right? The hard part always is showing that this neighborhood U bar, right, can be chosen to be a valid domain of extension for every control in that neighborhood. That's always the hard part, and that's where this comes in. Yeah, exactly. Yeah. Okay. All right. Okay, So, what I will start by doing is just talking about a very general discussion about sheaves and presheaves of sets. So I will sort of give the definition. Sheaf theory is really intimately tied in sort of any moderately advanced treatment with category theory, and I'll sort of illustrate slightly where that comes up. And so when I say sheaves and presheaves and sheaves of sets, really this can be done for any category. The definitions I give will be in the category of sets, and I'll just sort of indicate how that works in general. It'll be more or less obvious. But the intuition about this can be gotten by thinking about sets. And okay, that's an S, by the way, and it stands for topological space. And so I want to keep track of what the open sets are. So a presheaf of sets over S is a family. Okay, so I'm going to have a family of sets, okay, indexed by open set. Okay, so U is in O S. Okay, so for each open set, I have a set which I call F of U, and the assembly I call F. Okay. And so you have restriction maps, okay? And so that means that if V is contained in U, okay, both of these are open. So U is an open set, and V is an open subset of U. And what you have then is you have a restriction map, R, U, V, which maps F of U into F of V. Okay. So for sets, okay, so when I'm talking about a presheaf in the category of sets, okay, these are just maps. If your category has some structure, then these maps will have to inherit the structure. So in algebraic cases, they have to be, homomorphisms which preserve the algebraic structure. In topological cases, they should be continuous, and whatever else you need. Okay. All right, so you have restriction maps, and these restriction maps need some properties. Okay, the restriction map from U to U is the identity, and okay, and restriction maps commute with composition. Okay, all right. Okay, and so again, in the so let me say that how you phrase this after I disagree with this way of thinking about things as an initial way to present the definition of presheaves, but once you've seen the definition and become comfortable with it, a sophisticated way to think about what a presheaf is as follows. You have a category. Okay, here I'm talking about the category of sets. You have the category of open sets on your manifold, okay, whose objects are open sets, and whose morphisms are inclusions of open sets. So morphisms are only defined between open sets, one of which is a subset of the other. Okay? And then what you say that will leave a reader seeing this for the first time baffled is you say that a presheaf is a functor from the category of open sets into the category C. And if you work through it all, this is what it means. Okay? All right, so that's what a presheaf is. So I'm really not going to be considering many examples because there's very few examples that we're actually interested in. So the example I'm going to consider is the presheaf of vector fields. Okay, and so I'll call this G, and so these will be C new vector fields. We're going to maintain this regularity. Okay, and the notation I'll use for that is, this is a script G, okay, which mirrors that gamma there, okay, Tm. Okay, and so therefore, the definition of this is simply that G new Tm of U. Okay, so the set that I define corresponding to an open set U is just the set of all vector fields on U. Like that. Okay? All right, so these are vector fields on U. These are not vector fields on M, they restrict to U. Okay, so it's entirely possible that you'll have such a vector field which is not the restriction of a globally defined vector field. Right? And it's no problem. That's part of the definition. Okay. So what that amounts to is the statement that this restriction mapping is generally not going to be surjective. Okay? All right, so that's a presheaf. Right? So a presheaf is about open sets, so things that are locally defined. Okay. Now what we want to talk about is a special kind of presheaf which has two properties. So there's two conditions that you need. Okay. The first condition is this. So if U is an open set, okay, if UA is an open cover of U, okay, and if S and T, okay, so what you say in terms of terminology about these things, you say that these are local sections of the sheaf, presheaf F over U. Okay, so you have two local sections S and T, which have the property that their restrictions to all of those UAs agree. Okay, then S and T agree. Okay, it's hard to think of something where that doesn't hold, and for many, many presheaves, and all of the ones that we're going to talk about, that condition sort of automatically holds. Okay, so this is what's called the separation condition. All right, the more interesting one that doesn't always hold, and for which it's easy to find examples where it's not true, is what's called the gluing condition. So it says this. So if you take, again, an open set U, an open cover UA, okay. And you take, what you take is you take local sections defined over all of the components of the open cover. Okay, so I have an SA in F of UA. Okay, so you do that for each A, and then you have some sort of compatibility conditions between these things. Okay, so what the compatibility condition is that if you take S, A, and you restrict it to the intersection of UA and UB, okay, and then you do the same thing with SB. You take SB and you restrict it to UA intersects UB. Okay, and that has to be true for every A and B. Then there exists a local section over U that agrees with all these guys. Okay. And this is what's called the gluing condition. Okay, so let's look at two examples. So the first example will just be the declaration that this presheaf is a sheaf. Okay, and I encourage you to check that if you don't see that immediately. It's not difficult at all. So what you have to do is construct that that section S, and it's obvious how you do that. Okay, so let's look at something that's not a sheaf to give us some intuition about how this works. So it's going to be something that fails, satisfies this condition, but fails this condition. Okay. So what we're going to consider is the presheaf of bounded vector fields. So I'll tell you explicitly what that means. Okay, so it means that G new TM bounded U is the vector fields on U. So that this function, x maps to the norm of x of x. Okay, so this norm means relative to the Riemannian metric G is bounded. Okay, so that's a presheaf. So I should have said here what the restriction mappings are. The restriction mappings are restriction, right? So these are all maps, so it's just restriction of maps. Okay? Restriction mappings are not always restrictions of maps, but in this case they are. Okay. All right, so you can see that that will be a sheaf of sets. Okay. Sorry, a pre-sheaf of sets, but it's not a sheaf. Why? Well, it satisfies this condition, that's easy. But it doesn't satisfy this condition. That's relatively easy to see. Take M to be non-compact, okay? And cover M with a countable number, let's say, of relatively compact open sets, okay? And on each of those relatively compact open sets, you're going to define a vector field that's bounded. Okay. Well, in fact, just do the following thing. Take a vector field on all of M that's not bounded. Okay. Then, if you take that unbounded vector field and you restrict it to each of these elements, these relatively compact elements of the open cover, those will be bounded. Okay, because it'll be a bounded function defined on a set whose closure is compact. Okay, but there will not be a global section which agrees with that, because the global section will be the unbounded guy that you started with. Okay, so that's an example of a pre-sheaf that's not a sheaf. Okay. So this sort of gives you some insight into the distinction between pre-sheaves and sheaves. So pre-sheaves that are not sheaves, the condition to be an element of the pre-sheaf, what it tends to do is it tends to put restrictions that when they hold locally, do not necessarily hold globally. There's lots of examples we know about that, right? Integrable, right? So integrable is a concept which, if it holds locally, does not necessarily hold globally, right? So it can hold locally on a small enough interval, but when you consider an unbounded interval, it will not hold globally. So if you want to talk about sheaves, you should not be talking about integrable, you should be talking about locally integrable. Okay, same thing with Lipschitz. Okay, you can have a function which is the set of Lipschitz functions. Okay, so if you take a function that's Lipschitz on a bunch of small open sets, okay, it may not be Lipschitz everywhere. So when you want to talk about sheaves and not pre-sheaves, you should talk about locally Lipschitz functions. Okay, so sheaves sort of force you into talking about things for which the passage from local to global gives you something well defined. Okay. All right. So those are examples of sheaves. Okay. Okay, so associated with every sheaf, pre-sheaf, is an important object called its etale space, right? And it's defined like so. And so when I say pre-sheaf, you should always be thinking two things. You should be thinking that I'm really talking about a pre-sheaf of sets, and also that this could actually be a pre-sheaf of things in any category. Okay. S. Okay, so for the time being, we'll stick to talking about topological spaces. So I take a point X in S. Okay, so n sub x will be the set of neighborhoods of x. This is a directed set. Okay, and the order is, of course, larger means smaller. Okay, so if V is contained in U, then V is larger than U. Okay, so larger means you're kind of funneling down to X. All right, now take two open sets, two neighborhoods of X, U and V. Okay. And S is a section of F over U, and T is a section of F over V. Okay. So we'll call these equivalent. So S, so we'll say S and T are equivalent if there exists some W, which is a neighborhood of X, with W contained in both U and V, and our U W S is R V W. Okay. Now, if you think about this for a second, so let me finish. Okay. Denote by X the set of equivalence classes. Okay, so this is the stock of F at X. Okay, and an element of the stock. Okay, so what's an element of the stock? Well, it's an equivalence class, so it's represented by some local section defined over some neighborhood. Okay, so let's write that. Okay, so it's a local section S over some neighborhood U. Okay, very often I don't want to keep track of the neighborhood U, but let's do that for the first time here. So this is called the germ of S. Okay, so the stock is the set of germs. All right, so now, all right, so this is the set of neighborhoods is a directed set. And if you think about what this construction here really is, and you go off and you figure out what the words mean, the stock is the direct limit in the category that you're dealing with. Here is the category of sets over this. So let me say it this way. I can write this down. Okay, so Fx is the direct limit, okay, of these guys, where U runs over the neighborhoods of X. Okay, and so direct, as long as your category has direct limits, and all of the categories that we will be talking about have direct limits, okay, this definition of stock makes sense. All right, but concretely, in the category of sets, and for all of the examples that we're going to be talking about, this equivalence construction is the one that you should have in mind. Okay? All right, so that's stock, and the etale space of the presheaf F is just the disjoint union of all the stocks. Okay. Now, the etale space is endowed with a natural topology called the etale topology. And it's going to be useful for us. Okay. All right. It is a topology, and I will tell you what the basis for the topology is. Okay. So the basis is indexed by an open set U, and I'll write this down, an open set U of S, and a local section of S defined over U. Okay. And what is this basis set? Okay, so what you do is you take the local section, there's a little piece of terminology that I forgot to define here. I'll do it right here. Okay. It's convenient to use this notation. Our Ux of S is the equivalence class of S U. Okay. So if you have an open set U, which is a neighborhood of X, and a section S defined over U, okay, this is like the restriction map to the stock. Okay, that's what R sub U is. So what you do, you take all of the germs of S at points in U. So you go R, U, X, S, okay, where X runs over U. Okay, so that for a given U and a given S, that defines a subset of the etale space. Okay, so U is an open set, okay, and S is in F of U. Okay, so you have to verify that this does indeed define a basis for a topology. All right, so you have to show that, okay, but that's moderately easy. All right. All right, so there's a couple facts about, let me just fact for the time being. The map, pi f, okay? So pi f is going to be a map from the etale space, so it's the etale projection. It's defined like so. Okay, so pi f of, okay, so an element of the etale space is by definition an element of some stock. Okay, so the sum equivalence class, S U X is X, of course. Okay. So this map, if you equip the etale space with the etale topology, this map is a local homeomorphism. It's a surjective local homeomorphism. Okay. So here's the picture you should have in your mind about what the etale space looks like. All right. All right, so you have these stalks over each point X. You kind of are inclined to think of these as being fibers, and they sort of are, but it doesn't work in any way like a vector bundle works, because stalks of neighboring points are connected to one another by the etale topology. So if your manifold, or your, in this case our topological space, S, looks like that, okay? The way to think about one of these basis sets, okay, so I'm going to choose a U. Okay, so up here, going in this direction, I have the etale space of F. Okay, so what does this do? So this takes a section, okay, and at a point X, okay, it assigns the germ of your section at that point. Okay, so you take R, U, X of X. Okay, and so S is kind of fixed, and you do this at every point, and so you get some germ, and you can think of drawing the graph of the germ. So this is the graph of the germ. This is this object that I'm defining here. Okay, that I'm drawing here. That's B of US. B of US. Okay, and then of course the etale projection goes like that. Okay. All right, and just by the way I've constructed that topology, is formed by a basis like this. This projection will be a local homeomorphism. Okay, so the way you should think about the etale space is a little bit weird. So let me kind of redraw it here. All right, is over open sets down here. Okay, I have basis sets B of US. Okay, so for an open set down here, I'll have some basis set here, which will look like that. Okay, so for some other open set, I'll have a basis set like that. And these things can intersect in weird ways. Okay, and their domains don't have to agree. Okay, so the etale space is a gigantic thing generally, right? Because you're taking germs of local sections at every point in open sets. Okay, and each of these sets is open in the etale space. Okay, so these are all open sets. Okay, so these are not sitting in R2 and they're one-dimensional, so they're closed. No, these are by definition of the etale topology. These are open sets, and this is manifested by your requirement that all of these projections be local homeomorphisms. Okay. All right, so that's the etale space. All right. Okay, so. What about etale spaces for the sheaf of vector fields? Okay, so let me say some things about those, and I encourage you to go off and think about why these statements are true. Okay. All right. So take the etale space of vector fields of class C min. Okay, so the etale topology on here is Hausdorff if and only if you're in the real analytic or holomorphic category. Okay? So in all of the other cases, this is not a Hausdorff topological space. Okay. I think actually, sorry, for now that's the only thing I want to say. All right, so I think about that because it will help you think about what the etale topology is.
Is this house for etale topology or there's another topology?
It's the etale topology. Yes, you're thinking about the stock topology.
Yes.
Right, yeah. We'll talk about that, but this statement is true.
This is also true, right?
Yeah. Okay. All right. What time do I have, by the way?
10:20.
Oh, okay, then I will stop, sorry. Time flies when you're talking about sheaves. All right, so we'll pick this up next week, and I'll continue talking about all this stuff, and eventually we're going to also be talking about groupoids as well. So there's a little bit of abstract nonsense to cover, and then we'll see how all of this stuff relates to flows of vector fields.